Alright, silly people, here's the situation. This time we're going to be doing the discrete Fourier transform of another set of Dow Jones data, this time from 2004 to 2008, to illustrate the fact that things look weird if you just plug it into the regular Fourier transform program that we've been using. So you're going to need the dow2.txt file from the online resources. Just download that to your runtime. Go ahead and do that, and we can get into the problem. This is going to be pretty much exactly the same as the last two problems. It's just that the program isn't going to work as intended first. So let me create a variable called dow2, which is the numpy load text loading in dow2.txt, and then just go ahead and plot it just so you can see what it looks like. So it's different, and the main difference is that in the dow.txt plot from yesterday, this value started in the middle and it ended in the same place. They both ended up at like now 9,000 or something. For this one, they start and end at different places. So if we just do the Fourier filtering strategy we've been doing so far, where we calculate the Fourier coefficients with numpy fft.rfft, running dow2 through that, and then setting all but the first like 10% or 2% of those values to 0. So let me create a variable called L, which is going to be the length of the C dow2, and then create a variable called cut, which is the integer of that length divided by 50 to get the first 2% of the data. And so just set all but those first 2% to 0, then run it through the inverse Fourier transform, C dow2, and then plot that on the same thing and see how we get these weird artifacts on the end pieces, right? So here the smoothed version of the graph is coming all the way up here at the start and going all the way down there at the end. And again, that's because the FFT, RFFT function, whenever you do it like that, and then inverse Fourier transform it, the thing has to end up being periodic. So it does have to end up starting and stopping in the same place, assuming that the data was doing the same thing. That would be fine, but it's not. So the solution to this is to use discrete cosine transform, which is very close to the same thing, but not quite. So what I'm going to do is I'm going to copy this cell down here, and on this line, first of all, I'm going to get rid of it, and also I'm going to write in the discrete cosine transform function from the book. So it is just on the book, it's not on the online resources, so you do have to type it up. So I didn't mind just typing it up here. Then y, and then y2 is the empty array of size 2 times n float values, and then you run for n in range n, and then y2 indexed by n will become equal to y indexed by n, and then y2 indexed by 2 times n minus 1 minus n is equal to y indexed n. What this is essentially doing is it's taking the function that you started with and then mirroring it for another 1,000 values, and then creating a list of Fourier coefficients, which is again just the Fourier transform of y2, and then taking that and running it through an exponent minus 1j times pi times numpy dot a range. That better be numpy dot pi n over 2 times n. I'm not real sure what that line is there, but it is going to return the real version of, or not the real version, but the real components of phi times c indexed colon n. So that whenever you plot, or whenever you create c dow 2 and instead have it be running through the function dct, and if you plot the entire thing, you're going to get a symmetric function where it does still end up starting and ending in the same place. It's just that now the first half represents the smooth version of the data, while the second half represents, the inverse of that data. It's flipped. So what you can do at this point to really see the behavior in detail, you can set an x limit to 0 to the length of the original data, and now you just have the smoothed version of the graph, which is a lot better than just running it through RFFT naively. So yeah, kind of interesting.